In order to understand the difference between speed and velocity, I also need you to understand this thing between distance and displacement. Distance is how far you travel from start to finish. As a result, distance is always going to be a positive number. So think to yourself, like, if I had one of those cool smartwatches and it tells you how many steps you took, that's proportional to the distance you traveled. Distance is the total length traveled along a whole path. That means distance is a scalar. It doesn't have any particular direction because sometimes you were traveling north, sometimes you were traveling south, and distance is always going to be a positive number. The other word, the very similar word, is called displacement. Displacement is going to be that distance, but it's only going to go along the very shortest path between where you start and where you end. So I've seen some people write this as x, the displacement, is the difference between the final and initial position. You and I are only going to deal with displacement when it comes to like things moving in one dimension. I'm not going to make you do displacement or distance going in like big crazy paths like the one that's shown here. Now, displacement definitely has a direction. In this case, the displacement direction is down and to the right. Since it's just one line, it has an angle. And I could go and like figure out that angle if I wanted to. So how do I tell apart speed and velocity then? Is the difference between distance and displacement. Right? So, example. Let's say I go run a marathon. Right? Fun fact, this is the marathon track for the Olympics. How big and winding it is. That's a whole city they're talking about. When you run a marathon, what's the distance you run? 26 miles. Or if you're used to this in kilometers, right, it's something like 42 kilometers, right? So they run 42 kilometers, they run 26.2 miles. The distance they travel is 26.2 miles. What is the displacement? What's the difference between their starting and ending position? 0. So let's say you go run a marathon and you're all accomplished. You're like, yeah, I ran 26.2 miles. Your displacement is 0. If you start and end at the same place, then the distance you are from where you started is 0. So when I go take this to speed and velocity, speed is distance over time. And you can feel pretty accomplished about your speed. Speed's always going to be positive since distance is always positive. So this was the 2.45 hours. That was the women's gold in the marathon this year. So she ran 26.2 miles in 2.45 hours. That's 10.7 miles per hour on average. Have you ever run that on a treadmill? I think the fastest I've ever run on a treadmill is like 8 miles an hour. And that was like me worrying I'm gonna fall off the whole time. This is her keeping up a 10.7 mile per hour pace for 26 miles. That's insane. And she can feel really accomplished at the end of it because you're looking at that and you're like, wow, that's a really good pace. Right? But that's because speed and distance are scalars. They never cancel out. They can never be negative. If I told her her velocity, I think she might be like a little disheartened because velocity is displacement over time. And her displacement was what? Her displacement is 0 because she starts and ends at the same place. So gosh, that feels really disheartening. You're in 26.2 miles. Yeah, average velocity 0. And that sounds weird, right? Because you and I use the word velocity colloquially, like normally in our language, velocity is different than speed. Velocities can be 0. They can cancel out. They can be negative because your displacement can be 0. Your displacement can be negative if you went to the left instead of right, or down instead of up, or south instead of north. Okay. I like to remember this because speed and scalar both start with S, and velocity and vector both start with V. Speed is a scalar, velocity is a vector. So if you're wondering, how can it be that her average velocity is 0? There's a little segment of the race we can look at. Right? I'm gonna skip that. I'll come back to it. There's a little segment of the race we can look at. So do you see this little horizontal section right here? That's a good example of somewhere where her velocity to the right, when she was traveling along the purple path, cancels out her velocity to the left when she's traveling along the orange path. Velocities have direction, and so they canceled out. She ran all that way for a net velocity of 0. With that being said, let's recap scalars and vectors for a second to make sure you know the difference. Then you can like highlight that speed and velocity, displacement and distance are in here. All right. So just to recap, I know we talked about this when we originally did scalar addition, but a scalar is just a number with a magnitude, a strength. Things like time. I can have 30 seconds, or 5 kilograms, or 3 liters of soda. I could have a fever of 101 degrees Fahrenheit. I can have a speed of 65 miles per hour. All of those quantities, and you don't have to write them all of those quantities can't be negative. You can only have positive numbers of time. You can only have positive numbers of density. Okay. And so they don't cancel out. Right? If you want to think like energy, I can't add this kinetic energy plus that kinetic energy. Maybe it's like 2 football players running at each other. I can't take their kinetic energies and cancel them. All that energy just turns into some other form of energy, turns into something else. But vectors, right? Like velocity, these things have both magnitude and direction. And they totally can be negative. Like if I run to the left, that's fundamentally different than running to the right. And since I can have negative quantities, that means they can cancel each other. Technically, anything that's a vector, you could use that vector addition thing for, where if they go in the same direction, you add them, opposite direction, you subtract them, and perpendicular, you Pythagorean theorem that. You Pythagorize that. So again, you don't need to write all the examples of vectors, right? If I had to like highlight just the ones you need to know for this unit, I would say something like for scalars, you should know time, mass, distance. I didn't get a chance to write distance, and speed. For vectors, you only need to know velocity, acceleration, force, right? Maybe we add in the distance and displacement in there. Distance is a scalar, displacement is a vector. Fun fact, if you want to if you want to take a look at this slide later, if you go to the follow along slides, this whole thing is on one of the later slides. So last idea to leave you with, we've done speed, velocity, distance, displacement, scalar, vector, average versus instantaneous. Last one for today. All right. Last one for today is acceleration. Right? You'll see accelerations over there on the vector part of it. And we had an earlier problem with positive and negative acceleration. You could tell something was accelerating because it was either speeding up or slowing down. So next unit, we'll actually go and calculate acceleration. For now, you only need to know that an acceleration is caused by a changing velocity. And there's 3 ways you can do that. You can accelerate by speeding up. You can accelerate by slowing down. In physics, you know how you might use the word decelerate? In physics, we just call that negative acceleration. So we could speed up, We could slow down or change directions. When we get to unit 3 and we do circular motion, we'll go more into this changing direction thing. For now, you can think like, all right, speeding up. That means I have more force to the right than I do the left. My acceleration is to the right. And this person's accelerating to the right with their velocity to the right, so they're getting faster and faster. If you look at the picture, they travel more distance every second. Their dot diagram has dots that are faced farther and farther apart. So we could speed up. We could slow down. This might be something like the drag force takes over. It has more force to the left than the right. It's accelerating left, even though the velocity is to the right. So it's slowing down. Finally, the changing direction one. And this one is the one where, like, you should know that changing direction causes a change in velocity. You're not going to need these actual directions quite yet. This changing direction one, I want you to think of it as velocity has a direction. If originally the B is going up and to the right, and now the B is going down and to the right, well, that's a change in direction and therefore a change in velocity, right? Whenever direction changes, velocity also changes. So that's a special type of acceleration that we're going to come back to, and it's called centripetal. So if you take a look at the B with the blue arrow, the B with the blue arrow has a velocity that's down and to the right. But because it has a centripetal acceleration that points towards the center of that circle, it's going to change its direction. If you look at my circle, I tried to draw them nicely. They came out okay. The acceleration points to the center of the circle. The velocity points to the side of the circle. And since they're changing direction, those two are perpendicular to each other.